This is from our Open Intro textbook. Problem 4.39, we have the weights of pennies. Let's see, so the distribution of weights in the United States is approximately normal with a mean of 2.5. Notice it just says the distribution of weights of the United States pennies. That makes me think it's for my entire population. Okay, and so my population will have a mean of 2.5 and a standard deviation of 0.03, and it tells me it's approximately normal. Not exactly, but pretty close, approximately normal. Okay. So part A says, what's the probability that now when it says that that means just one penny. We're not talking about a sample, just an individual value. So a randomly chosen penny weighs less than 2.4 grams. So we're talking about an individual value. We're looking for the probability that one penny weighs less than 2.4 grams. This is, notice it says it's a normal distribution, and if we have a normal distribution, we can use the normal probabilities for an individual value. So I always start by drawing a picture. My average is 2.5, so 2.4 is probably about here. X equals 2.4. I want the probability to the left. So I'm going to use my table or my calculator. I'm going to use the normal CDF, make sure CDF and not PDF function. Now you need bounds, so my lower bound, let's see, I don't have a lower bound, so let's just put in some ridiculously small number like -1 billion or something. Just lots and lots and lots of zeros there. My upper bound is 2.4. My mean is 2.5, and my standard deviation equals 0.03. So put all of this into your calculator, and you should get the probability that x is less than 2.4 should be equal to 0.0004. Now B says describe the sampling distribution of the mean weight of 10 randomly chosen pennies. So now we're talking about a sample mean. Okay, for your distribution, you're going to have three things you're worried about. Your shape, well, our original distribution was normal. And so that means for any sample size, the sampling mean will still be normal because, again, my original distribution was normal. You want to worry about the mean or the center. So the mean for your sample means will always just be equal to your original population mean, which is 2.5. And your standard deviation for all of your possible sample means will be equal to your original standard deviation over the square root of n. So our original standard deviation is 0.03, and then it told me we're doing a sample size of 10. So 0.03 over square root of 10 gives me 0.00547. You might notice if you look at the textbook answer, they accidentally put over square root of 30. There's no reason for this. This is just a typo for them, or maybe they changed it between editions. So kind of ignore that. This is the correct answer because they did say our sample size was 10. We want to take a sample of 10 pennies. Okay, so that's your sampling distribution. Now C says, what's the probability that your average weight of 10 pennies is less than 2.4 grams? So for C, notice again, we're talking about our sample mean. Okay, we want the probability that our sample mean is less than 2.4. So again, we'll do the same thing. Here's my 2.4. That's my sample mean, x bar equals 2.4. We want the area to the left. Everything is almost exactly the same as up above. We'll use our normal CDF function. That's what we always use to find areas or probabilities, okay, if it's a normal distribution. And we'll still do our lower bound of like -1 billion or something. We'll still do our upper bound of 2.4, but my mean, well, let's see, my mean is still 2.5, but this is where it changes. My standard deviation is 0.00547. So let's put that into our calculator. So I'm going on my TI-4 to go to second distribution. I want my normal CDF. My lower bound is -1 times 10 to the 99. That's a really low number. I can leave that. My upper is 2.4, my mean is 2.5. The standard deviation for sample means is 0.00547. And it tells me 0. Let me try a better calculator. If I use an even more powerful calculator, I find that the probability that my sample mean is less than 2.4 is equal to 5.8 times 10 to the negative 75. So this is a decimal with 74 zeros in it. It's no wonder my TIA calculator just said 0. So you might be asking yourself, why is this so different? Why do we get such a different answer between A and C? So you'll notice up here in part A, the probability that just one person was less than 2.4 is 0.004. But the probability that our average of 10 people is less than 2.4 is all the way down to basically 0. So what is so different about this? This is our whole point between what's different between individual values and sample means. So it doesn't say to do part D, but I'm going to go ahead and show you this in a general sense. So if this is my original population, or my individual values, we're centered at 2.5, and here's my 2.4. So the probability that I'm less than 2.4, actually I don't think I have that quite to scale. Here's my 2.4. So there's some kind of probability that you're less than 2.4 for your individual values. But then if we keep it on the same scale, the distribution for all the possible sample means looks much more like this. It's always going to be skinnier. That's because your standard deviation is smaller. So here's my same 2.4, but notice this probability is going to be much smaller. Okay. So this is the distribution of all possible sample means. So the probability that you get something kind of far away from your population mean will always be smaller the bigger your sample size is, because the standard deviation, the variability, gets smaller and smaller for sample means as n goes up. And part E tells me, or asks me, could you estimate the probabilities from A and C if the weights of the pennies had a skewed distribution? So in our case, we could find these probabilities for our individual values because my original population was normal. So for individual values, you have to have a normal population. So if it was skewed and not normal, I couldn't use the normal distribution to find these probabilities. And for C, what's the probability for our sample mean? Well, for sample means you either have to have normal or a sample size of at least 30. But our sample size was only 10, so I wouldn't be able to find that probability either. So let's go down and write that. So for A, for probabilities for individual values, you can only use the normal distribution to find probabilities if the original population is normal. So if it was skewed, we couldn't do it. Okay. For B, for probabilities for sample means, you can only use the normal distribution to find probabilities if the original population is normal or the sample size is at least 30. But in our case, if it was skewed and n is only equal to 10, we couldn't do it. We would have to use some other technique.